So what we're going to do today is I'm going to explain to you how a pulse oximeter works. Did I bring my pulse oximeter again? Still in here? Yeah. So the pulse oximeter is this amazing device that you can, it's a non-invasive device, right? You can put it on your finger, sometimes there's a cable on it. My watch has one as well. And it tells you how much oxygen is in your blood. So we're going to explain how that works. And it reports it as something called SpO2. So by the end of today, I'm hoping it'll be intuitive. Now the underlying principle behind it is something called the Beer-Lambert law. And we talked about it last time, right? So I'm not going to spend too much time on it, right? But if you weren't paying attention, here's the review, right? You have a light source. You have a vial filled with some sample. And then you have a light detector. And we talked about last time, this could be an LED, this could be a photodiode, but right, there's some way to measure how much light is coming out at the other end. This would be your sensor, right, in fact. And Beer-Lambert tells us that if you take the amount of light that's coming in and you measure the amount of light coming out, they're going to be related by this, which is E to the negative, something called absorption, which is how much light is absorbed. And the bigger this is, the less comes out. Now, what's useful is Beer-Lambert tells us what the absorption is. The absorption is the concentration of material in here, right, like moles per liter, molar, times the extinction coefficient, or absorption coefficient, which is a constant, a number like 3, times the length, right? So you have concentration, E, and that. Now, this is known because we measure it, and this is known because we put it in, and this is known because you look it up, and this is known. And so by using this technique, you can actually figure out the concentration of A inside of it. Okay. The other thing we talked about, put it here, maybe, is if there are two materials inside, call that A and B, essentially each one contributes independently to how much is absorbed, right? A is doing some absorption and B is doing some absorption. And so we get a slightly modified equation which says I is equal to I sub 0 E to the minus, and what we're going to put here is the contribution from each one. So this could be the concentration of A times the absorption coefficient of A times L plus the concentration of B plus the extinction coefficient of capital B, B times L. So you can see we're adding in these two terms. Now, if this one is 0, like it has 0 concentration, well, it just won't contribute, right? Which makes sense. Okay, so this is really just a case of this situation. Now, if there were 3 things, C, you would just add a C. So you would keep adding it in. Okay. Now, what I'm interested in is to do this. I illustrated for a fingernail, but it's nice to imagine a finger, right? But you could imagine it's like a tube, but you could do this through the earlobe or somewhere else. I want to do a situation where I shine a light I0 into the finger, and I detect, again, this is the detect, right? The light coming out. And I want to use this to know the concentration of something, right? Now, the thing I'm particularly interested in know the concentration of is the amount of oxygen in the blood. Now, it turns out that there's two, and so there's blood in here. Okay. Now, you know, from your physiology class, very important that blood picks up oxygen from our lungs and delivers it to all our organs, or we die very quickly. There's two ways the blood can do that. One is it can sort of dissolve the oxygen inside the blood, like bubbles in like a soda, right? Where the bubbles are there, you open it up and the bubbles are kind of inside of it, right? It turns out that that's not very efficient because it can't absorb that much oxygen. So nature, right, or God, depending on your point of view, right, created something called hemoglobin. And hemoglobin, H lowercase b, sticks to oxygen to make oxyhemoglobin. Okay, so this one is called deoxyhemoglobin because it doesn't have it, and this one has it. So what happens is that the hemoglobin in your blood can grab onto a lot of oxygen, and it carries that oxygen attached to it, and then it releases it as needed. So when we're talking about how much oxygen is in your blood, we're really concerned about how much oxyhemoglobin you have, right? Though this is also related to sort of how much oxygen you have dissolved, all right? So very, very important physiological metric. And there is when you get a report of SpO2, which is how much saturation of oxygen you have in your blood, it is in fact a percentile of the concentration of HbO2 over the concentration of HbO2 plus the concentration of Hb times 100. And so you can see, right, and this will be reported as a percentage. And so you can see how if you have 100 units of this, right? Sorry, 100, well, and the Hb total is going to equal to the sum of the deoxyhemoglobin plus the oxyhemoglobin, right? So you have a total amount to work with, and it can go through these two stages. If you have 100 to work with, we could do, 99 and 1. In that case, you would have 99 over, well, 99 plus 1, we know it's 100, so you would be at 99% saturation. So that's why it's reported as a percentage. And this is what you have to work with. Okay. So I'm going to put a square around this. It's going to be important. This is the thing that we want to extract. Okay. I want to just give you a couple corollaries of this, which right now may not seem to make much sense, but they're going to be very useful later. We can say that the concentration of oxyhemoglobin is equal to this SpO2 quantity times the Hb total. And we can also say that the concentration of deoxyhemoglobin is equal to 1 minus SpO2 times the concentration of Hb total. These are just things that you, just substituting this into here, you can derive these sort of secondary quantities. And this is not useful to us just yet, but just put it in your pocket, right? We're going to be relying about this. So you could express both oxyhemoglobin and deoxyhemoglobin as a function of this SpO2 and Hb total. And you're saying, well, I don't really like that because SpO2 is itself a function of these parameters. It's not useful in its own sense, but it's going to be useful to us in a little bit, okay? All right. So here's a quiz. Let's do it right here. Do it in green. Here's your quiz. I'm going to do it right here. I'm going to give you a table that is the extinction coefficient, and this is in centimeters per molar, of oxyhemoglobin and deoxyhemoglobin. And I want to give it to you in terms of two frequencies, right? Because I said these are a function of frequency, right? So the first one I'm going to give it to you is in terms of red light. And the frequency of red light is expressed as 660 nanometers. Now, is it capital? No. Now, you're going to say, well, nanometers isn't a frequency. Frequency is like 10 hertz or 50 hertz, right? People will actually refer to this as not the wave frequency, but the wave length. But it's directly related to frequency, all right? And we're going to use this because this is conventionally how you're going to see it. But you should understand that this is a expression of frequency. 1 over this, all right, with a speed of light correction is that. If you say, well, why don't they just give frequency? I think honestly one reason is the frequency would be a big number, like a billion, gillion or something like that, and people don't like to do that. Well, this is a more, I think maybe that's one reason. And so it turns out you get numbers here of, these are actual numbers, or I believe these are 3.2 times 10 squared, and this one is going to be, by coincidence, also 3.2 times 10 to the third. And you'll notice that this is larger than that, in fact, by a factor of 10, right? So in red light, there's a difference, right, in how well they absorb, right, where this one is absorbing more. Okay. Now, at infrared light, and I'm choosing infrared specifically for a reason, right, but I could have chosen green. So we're going to call it infrared, which is at 940 nanometers. The absorption is 1.2 times 10 to the third and 6.9 times 10 squared. All right, so this gives you here, put a box around it, some data that you can work with, right? And we'll look at this data later. Okay, now here's the question. Let's say again, these are actual numbers, that the concentration of oxyhemoglobin, so I'll be using this sort of C notation sometimes for concentration, okay, but you can look at bracket, is 2.2 millimolar, and the concentration of hemoglobin is 0.07 millimolar, and these are healthy amounts. You'll notice you have much more in the oxy state than in the deoxy state, all right? So this is what I'm going to do. I'm going to take the blood out of your body, right, make sure that everything is stable. I'm going to put it in a vial, and that vial is going to be 2 centimeters long. right? I want you to give me the equation relating I, which is the light in, right? I0, which is the light in, to I. I'm essentially just asking you a trick, okay, to rewrite this equation with the appropriate things. But there's one thing you need to ask me, right? What's the bit of information in order for you to plug in the appropriate values here, what is one more bit of information I need to, right, epsilon. Now I could say, but I gave you epsilon. So why, what else did I, and this is the real what else is missing? Give me the answer. Why can you, and by the way, I don't need you to solve this, just write it out. Okay, just write it out. I don't need you to actually solve the math, right? Just give me the equation. What else is missing? Can you just do it? Go ahead, write it out. So I need, fill in all the, I gave you that, right? I gave you all the numbers. So just write this out, but fill in all the numbers. Is something missing? Well, go ahead and start to do it, and then you tell me. Okay, just write it out and we'll pass it in. So all I need you to do is give me this and just plug in the, you do not need to solve, right? You don't need to combine terms or do the E, right? Just write it out. Yes? What's that? What do you need, what about the I naught? Write it in terms of, just leave it as I naught and I, right? I did not give you I naught. If you want, you can take it as, let's make it simpler. I naught is 10, whatever units those are. Yes, what else is, so now you're done or you need something else?
So the things you wrote there are the concentrations of A and B, and A being HbO2 and Hb being B.
These are the concentrations right here. And these are the lookup table, if you will, of their extinction coefficients, which would be there irrespective of the concentration, right? So whatever concentrations we have, this is more like a material property, so it will not depend on the concentration, okay? So can you now give me the equation?
To be clear, that I naught is the same value for red and infrared?
So the I naught, you're asking me, is I naught the same value for red and infrared? Sure. Let's say I naught is 10, irrespective of red or infrared. But I think you're starting to ask something that, okay, so you're saying, do you want us to do two equations? Why are you asking that? Right. So when you're plugging in here, and this is really what I wanted you to get out of it, right? You can't solve the problem because I didn't tell you what frequency. I didn't tell you what frequency, right? Because if you used red, well, whoop, looks like deoxy is doing a lot of work for you here, right? But if I picked infrared, well, it's a different value, right? The math's not going to come out the same. So let's pick red light. Now you should have all the information you need to write this equation out, and you don't need to solve it, but this will be it's all going to be numbers, right? So go ahead and now you have the information. Okay. So this is how you could have approached this problem. You could have said, I got it, and I'm going to write it without plugging in the numbers, okay? Because I want it in this pure form, right? You would have said I is equal to I sub 0, right, times e to the minus, and now what we're going to, we're going to keep it as a big bracket. All right. What we're going to do is we're going to take the, let's write it this way. Minus, we're going to take the first concentration. Let's do the concentration of oxyhemoglobin, right? We're going to multiply that by the extinction coefficient, of oxyhemoglobin at red, right? And we're going to multiply that by the length. And then we're going to have another term here, right, which is going to be the concentration of hemoglobin, deoxyhemoglobin, times the extinction coefficient of hemoglobin at red, deoxyhemoglobin, I'm sorry, times the path length. And we could pull out the length, right? So we've just applied this equation here, right? And what you did, and you could have had the minus in front, right, and had these in brackets, but I did this here on purpose for a reason, and you just plugged in the values. And there you have it. Okay. Now, if I had given you this problem the other way and said I measured this much light out, right? We talked about this last time. So if I said, well, I'm not going to give you this. Okay, you don't have this. These are unknowns now. But I will tell you that I measured the light out, and it was 1.5. And so now, of course, I want you to give me the concentrations, right? And this problem is not well resolved, right? Because let's go over what we know and what we don't know. Know, right? Because I gave it to you, but in any case, we know this because we, wait, did I do, what did I call? I was confused. I out is in, right, and I is out. I out is in, I is out, yeah. Now, this is an unknown. This one here is a known. This one here was known in this case, so that's fine. But this one was unknown, known, known. And so we have a problem here where if I ask you to give me the concentrations, you don't know. Because it could have been 10 of this and 1 of that, or 15 and 3, or right? There's many potential numbers you can put in here to do that. It's a classic one equation with 2 unknowns. You guys remember that? Yes, last class. Okay. And do you remember what the solution is? You lose 2 lights. So let's go ahead and write the other equation. And so this, to be clear, was for red light. And so I could do the same thing for infrared. And in this case, I would get I is equal to I sub 0 times E. And then we're just going to rewrite this concentration of HbO2 times the absorption of HbO2 at infrared, different number, but still a number, times the length minus the concentration of deoxyhemoglobin times the absorption coefficient of deoxyhemoglobin at infrared light times the length. And by doing that, right, if I now and I have to give you now both the red and the infrared numbers, right, because these would not be the same numbers here. You would now have 2 equations and 2 unknowns, and it wouldn't be that bad to solve it, okay? And now you're thinking, well, that's it. That's it, right? I've solved pulse oximetry. I just need to make sure there's 2 light sources in here, right? One is on, the other one, right? Take turns maybe, red, infrared, each one takes a turn. And then this has a little processor in it. Well, it will detect the light, and then it will do a little bit of math that it will do it. Well, not quite, okay? So this is where we left last time. There's a little bit more to sort of this issue of pulse oximetry. One of them is, I don't know L. Do you know the length of my finger? You could guess. right? But you're not sure, right? And it may not be Emily's length, right? But that's not the least of our problems. We actually have a much, much bigger problem. And that problem is that in this vial was just two things, right? I said there's only two things in the vial, oxyhemoglobin and deoxyhemoglobin. But in my finger, there's more than two things. I have skin, and I have fingernail, and I have bone, and I have fat. Hold on a second. So in fact, I'm going to add here minus, let's go, right? Let's start adding these terms. But what I'm going to do is I'm going to put all those into one equation, and I'm going to call this tissue. And by that I mean all the other tissues. So I have tissue, I have absorbance coefficient of tissue at red, and I have this length, okay, and then let me do it here as well. So minus concentration of tissue times the I'm going to do length of tissue here. Of tissue at infrared times the length of tissue. Now, you have to imagine that this is the sum. It's like a sum, right, of all the tissues, one after the other. Tick, 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 tick. Here we go. Bum, 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 bum. So all of a sudden, we no longer have two equations and two unknowns. You have two equations and oxyhemoglobin, deoxyhemoglobin, bone, fat, another kind of fat, sunscreen. It's right. It's in the way, right? Sunscreen, marker, blah, blah, blah. Oh, we were so close. We were so close to having a pulse oximeter. And we lost it, unless, of course, you want to draw blood, but I don't want to draw blood. And it's even worse, because this length varies. You see, you have to factor in the bone, but even if my finger was 2 centimeters, the bone might be 1. But on Emily's, the bone might be 0.75. And my fat, right, might be 3 millimeters, but on Emily's might be 2 millimeters, right? And my skin might be 4 millimeters, and Emily's skin is 6 millimeters. So I even have that issue. But not only that, I don't actually know what Emily's skin thickness is. So unknowns upon unknowns. You have an equation. So I can't solve this problem. I can't solve this problem. Do you understand why? Like we almost had it. We're just there. We're about to reach it, and then can't do pulse oximetry unless I draw blood out. Okay, but there's a solution. And it's a very elegant solution. I want to go back to, I showed you this last time, about what it is you actually measure when you put light through the finger. And if you remember, we said, okay, here's time. And here's the amount of light that I see coming out, right? And it turns out that the amount of light, I'll do it in black, the amount of light you see coming out, I'm going to exaggerate it. Looks like that. I know why I don't want ticks. The amount of light you see coming out of my finger, right, if you had really good eyesight, it's red, but then it's like a little less, a little less. It's weird, right? It's almost like a certain amount of light is getting through, and then something else comes and blocks it, and then it goes away. And I want to mention this is small compared to the amount of light. It's small. You can't see it with your eye. This you could see with your eye, right, if this was correct. And we correctly identified this, and maybe I'll draw it in red, as reflecting blood that's surging into your body every time you beat. So this is blood, and this is the rest of the tissue. Because my bone doesn't go wah, 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 wah every time my heart beats. My skin doesn't go wah, 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 right? But the blood does. I mean, that's a bit of an exact, right, obviously tissue can move a little bit, but that's the basic idea. Now, I want you to realize that this reflects, I want to draw here. I want to label this as A. A is the overall absorption, right? So the way you understand this is that you have a level of absorption, and then the absorption, draw that neater, but the absorption is going up, right? Right, I mean, the reason the light intensity is dropping is because we're getting a bump in absorption, okay? That's what it means, right? One is up and the other is down. Okay. This is the blood. Very nice. Now, this is the signal coming out of here, right? We're detecting this light. We talked about using a photodiode, but we have this, right? So let's be clear now. This is a function of time. Right, it's a function of time now. And let's say I wanted to just extract this. Say, oh, that's it. Let's just go back to the heart rate example. Forget, I've given up on oxygen, but I would like to measure heart rate, right? And so what I want to do is I want to make it, for example, that I want to extract just this part that's changing. Let's say I do. Now, if it's coming out of the sensor, I want you to understand that I'm going to write this in units of, I know it's intensity, but I've converted it to volts. I think it's easier for you to realize. It's like 1 volt, 2 volt, 3 volt, 4 volt. It's coming, remember, the sensor converts the light to a voltage, right? So just think of this as a voltage. And what the voltage is doing, right, is the voltage is dropping every time the heart beats because there's less light coming in, right? And so the amount of voltage I get is dropping, right? If the light dropped all the way to 0, I would have 0 voltage. That makes sense? I want you to think of it as voltage. So we have this voltage sitting here. So we have a voltage here. These are a function of time. So this is intensity, and this is associated with the voltage. And what I'm going to, and this voltage is sitting on, it's a potential. And what I want to do is I want to extract the part that's changing and be left only with this blip. I want to have a situation where if what came in looked like that, I want to send this through a box. And I want the output of that box to be just the changing signal, right? And I want you to remember, I've drawn this. This is really, I don't know what, 100, 1,000 times bigger than this. So it's really, really very tiny. Okay, maybe it's not clear why you'd want to do that here, but imagine if this is a very, very tiny signal. And so I want to send this through a box. So it's a bit messy. Right? And I want the box to remove it. Now it turns out that the box you would use to use that is something called a high pass filter. You're saying the same high pass? Yes, the same high pass filter. It's always the same high pass filter. Okay, it's always the same. High pass, low pass, high pass, low pass. You're good with that, you're good with everything. Now, why would you use a high pass? And what I want you to think about is I talked about how we design filters without math, right? There was a previous lecture, and I did that on purpose. And I said, when you have a signal, and there's something slow in the signal, let me draw the slow part in the green, right? and there's something that's changing, right? And so the change is what's in the red, right? So one is really, really slow. I mean, it doesn't get any slower than the DC, right? You can think of it as a 0 hertz. This is a 0 hertz sinusoid. And then here we have another sinusoid. Let's say this sinusoid is 1 hertz. And so I know that if I want to separate these out, I need a high-pass filter, because a high-pass filter will let the thing that changes through and will let the thing that will not change get out. Does that make sense? So we're using a high-pass filter, and the high-pass filter extracts this. Now, what about the other way around? Could I, what if I just wanted to take the part that didn't change? Well, I would use another box. And that box is called a low-pass filter. And if I take this original signal and feed it into the low-pass filter, the outcome is, in fact, I'll put it in green, just the part that doesn't change, right? And I used red here for this. That's the intuition. Is there math to it? Yeah, there is some math to it. But that's the intuition that filters allow us to strip fast changing, slow changing. And in fact, you could do both of these, right? You can say fast changing goes here, slow changing goes here. Okay. This is done often in biomedical instrumentation. Now, I think you know why you want this. This doesn't seem very interesting right now, right? This seems like not what we're interested in, right? But we'll come back to this one. But okay, we have this one. That's nice. And this is just the things that are changing, right? See? What's changing? The blood. That's the thing I'm saying. We're going to assume that the only thing that's changing is the blood. What about bone? Oh, that's here. Does bone matter? It does matter, but it doesn't change. What about my sunscreen? Yeah, my sunscreen had an impact. But that impact didn't change every time my heart beats, right? So sunscreen is here. And I just stripped that out. And so you see, it's interesting, right? You learned about high-pass, low-pass filter, right? And we talked about EKG. But I said it's used for everything. It's used for every single biomedical measurement. Here you go. It's used here as well. You can take the part that you want and strip it out. That's the concept behind a pulse oximeter. That you realize, right? By the way, and so remember it says pulse oximeter. So you do the pulse, you get that for free, and then you do the oximetry. In both cases, you strip out the part that's changing. So we take this and we end up with just this part. This part, right, is this part. We just remove this. They could say, but I don't know how much bone you have. The beauty about filters is you don't actually, remember when they said the beauty of these filters is you don't actually need to know what the noise is. Let's say Emily has very thick bones. This will work. Let's say Emily has very thin bones. This will work. Let's say Emily put on an extra layer of sunscreen this morning, right? Because she's very conscientious about that. This will still work. So the power of the filters is they're incredibly powerful because you don't need to know that, right? And if Emily's heart rate goes up, right? If it goes from 60 beats per minute to 80 beats per minute, this still works because it's still high and it gets through. So I don't need to know Emily's signal. I don't need to know Emily's noise. I just need to know this general thing, right? That when it changes on Emily, it's blood. The power of filters, that we don't need to know this information. Yes?
I remember you had mentioned that in the States, because of the power lines, it's almost like 60 hertz.
There's also noise on top of it. So it turns out that there's this ambient room light here, and that will be picked up by the sensor, and that will be much bigger than this signal. In last class, I talked about using a carrier to get rid of it. And that carrier, let's say these lights are flashing at 60 hertz, I'll make that carrier 1000 hertz. So I can clearly distinguish the carrier from what's going on. And I also mentioned, I did this in passing, I appreciate it, that these things don't use sinusoids, they use pulses, all right? So what I'm doing now is ignoring that, okay? I'm ignoring that source of noise. So on top of everything I'm showing you today, you will also do that trick. So there's actually two tricks going on. One trick is the flashing light in order to create a amplitude modulated signal. I covered that last time. And now I'm giving you another trick, which is to look at what's changing. And in fact, you would do both tricks at once. So in reality, the light will be flashing like, the light is really going to be going, so if it's clear, right? The light is flashing like this, right? The light is really flashing, tick, 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 tick. And in fact, guess what? Red, infrared, red, infrared. So it's very convenient. You just take turns. Red, infrared. And that's what you'll see here. If you look closer, you'll see that the lights are actually flashing. And if you have, I don't know if you can see this, but it's actually alternating between two different light sources. You need one, and you can use the same detector, by the way. So theoretically, you can use two detectors, but you could also use one detector. I don't want to talk about that today because that is but I'm happy you brought it up. I'm really happy you brought it up. Let's put that as another layer of the onion. I just want to focus today on this part of it. So now I've just told you I have a way to get rid of all of this, theoretically. Now, there's a terminology that people use to describe what comes out of a low pass and a high pass filter. They will often refer to this as the AC signal. Or they will say that this is a AC coupled signal, alternating current. Now, it's not a sinusoid, but that's what they refer to. And I want to throw out this terminology. You know I don't give you a lot of terminology, but like you can't go out into the world and not know this, okay? And they will refer to this as a DC coupled signal. DC like a direct current, like what comes out of a 9-volt battery. So you may refer to this as the low pass output, and you can refer to this as the high pass output. But I want you to switch and start referring this to as the AC output or the AC coupled output and the DC coupled output. But I'm not introducing a new concept. This is just the output of a high pass and this is the output of a low pass. Okay? And so now what I want to show you is that if we look back at this signal, I'm going to label on here the AC and the DC. I'll do it in red here. So the AC component is here. What do I mean by AC? The part that's going to come out of your high pass filter. And that's a much larger component. And this is the DC component. All right? Now, okay. And now we have to do a little bit of work. Because okay, there's another problem. I don't actually know L. L would be something like the amount that Emily's blood vessels, the capillaries in her finger, dilate every time her heart beats, right? L would be that sort of, there's an influx of blood, and so Emily's blood vessels swell a little bit, right? That's what's leading to this transient change here, right? There's a surge of blood going into her finger. I don't know what that is. I really don't know. I have no way of looking into Emily's finger and saying 100.3 microns, right?
Isn't that solved by the two LED lights?
Okay, so your solution is this, yes. Yes, shoot, now we don't have to do the, no, we're still gonna do the derivation. Correct. You already know the solution because we have the two lights. But I need to show you that there is some additional, conceptually we're done. I need to show you how the math works out, okay? Conceptually we're done. Let's go through it. Now, before I erase this, I need to show you that this information is usually not, well, can be given in the form of a table. You'll usually see it in the form of a plot. And the plot looks like this. I'm just going to put it here. So what you have here is the extinction coefficient. And here you have the frequency of light, but it will be labeled as wave length. And the numbers you'll see will be things like 500, I'm sorry, no, I'm writing very small here, 700, 800, right, 900. And so, for example, we know that red is at this point here, and infrared is at this point here, all right? And there will be a plot for both hemoglobin and oxyhemoglobin, where oxyhemoglobin is going to look something like that. So this is going to be HbO2. And I mean, I'm drawing this roughly. And deoxyhemoglobin would look something like this. So this is Hb. Now, what I've done here is I just read off these particular values, right? There was a value here, there's a value here, there's a value here, and there's a value here. And you can see this crisscross. It's very important. This is going to come up. This crisscross is very important. People will call this the isobestos point where they cross. We don't go here because then we wouldn't be able to tell the difference, right? If we use only this frequency, they would remain. And so you'll see something like this, but I think it's just, you can just think of it as a table. But I just want you to be aware, right? You'll see, it'll be represented in this way, but now you know what that is. It's just, and remember, these are properties of the material, right? Make sense? I think it's easier to first talk about it like this and then present the figure. Okay. All right. So, as I mentioned, my son went to a Pokemon tournament on Sunday. So I had a bit of time to write this out. This is certainly not something I have off the top of my head. And as I told you, right, here's a news flash. It turns out that a lot of this, you don't need to know this derivation, right? Maybe you'll teach this class in 20 years, and then you'll go back to your notes. But unless you work at Pulse Oximeter Incorporated, right, or Samsung hires you, right, to work on their next pulse oximeter watch, then you'll definitely need to be familiar with this math. But I think it still does a nice job of kind of illustrating to you. You'll see it. I think it has some nice illustrative components. So what I want to do first is I want to consider, and this part here, when the heart is not beating, is called diastole. And when it is beating, it's called systole. From die, I think, is like to relax. Heart's relaxing. some sort of Greek term, and sys is somehow about contracting, right? And here you have to realize that the diastole is up the top, diastole, and the systole is the beat, right? Diastole, systole, right? And okay, now what we realize is that, let's imagine during the diastole, right, we don't have this, right, because the blood hasn't come in yet. We only have this contribution. And I don't know what it is. It's a lot of things, but what I do know that they all share in common is that they don't change. Right, so that's why I can group it as one. So what I'm going to say is that the amount of light that comes in the diastole stage, I sub d, is equal to what? Well, what equation I'm going to use? I told you the only equation we were going to use for this whole thing is Beer-Lambert. So I'm just going to write I sub d, this is a d. I'm just going to write that this is equal to the amount of light that comes in times e to the minus a static, meaning whatever is not changing. I'm just defining it that way, okay? And this is equal to I sub 0 times E, the sum of concentration, static, lambda, static, length, static. What does it mean? Don't worry, this is going to disappear, so don't worry about it. But before it disappears, let me tell you what it is. The concentration of bone times the absorption of bone times the length of bone, the concentration of finger substance in the fingernail times the absorption of fingernail times the length of Emily's fingernail, sunscreen, 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 and we just add them all up. That's what we did here. We have to add up these terms. But I'm only saying what about, I'm saying that during when the heart is relaxing, I'm going to do all those things that are just normally there, right? Including any blood that still happens to you. I'm going to just group it all. Now, and that is the equation for the amount of light I have here. Okay. Now, what's the equation for the amount of light I get through here? Well, it's going to be less, because let's look at it this way. Here is all the static, and then here I have the dynamic, right? So there's going to be less light when the heart beats, because everything that's there, fingernails and bones and sunscreen, is still there, plus blood, right? And to be clear, I should probably put this in the middle, because the dynamic is oscillating around it, okay? But so what I'm going to write now is that the I in the systole, which is equal to I sub s, is equal to, well, again, we only have Beer-Lambert. It's like before all we had is Ohm's law, so we just kept writing it. We're just going to keep writing Beer-Lambert. So this is going to be I sub 0 times e to the minus a static, plus a, I'm going to call it dynamic. What am I saying? I'm saying that the light that I get through here is going to be reduced by all the stuff that was there before, plus the additional thing, which is blood, right? And I could just rewrite that as I sub 0 E times the sum, I mean, this was a negative, the sum of all the static things and the sum of all the dynamic things. This is this, right? It's the same thing, right? You would have here our static, and we have, oh, and there's one more static, So here, and we have our dynamic. Okay. I don't think this is very illuminating at this point. Okay? I'm just kind of rewriting things. Now, the IDC is actually the I diastole. What do I mean by that? The intensity that I measure, the intensity that I extracted in the DC case, right, is the I diastole. I mean, I sort of defined it that way, right? The DC component is this, right? Let's say there was no blood flow. Let's say blood flow stopped. Oh, there's no more blood flow. Emily has no more blood flow, right? What would I be left with? I would just be left with this, right? And so, how do I extract? How did I extract the I diastole? Well, I sent it through a low pass filter, right? It's not a very interesting equation. It's just like 1 is 1. But now it gets interesting because now the question is, what is the AC component? What is the AC component? And this is interesting. So the AC component is, you may say, well, it's the I systole, but it's not. It's the I diastole minus the I systole, and that's the catch. Okay? It's this difference. You can't just say it's this value. It's not this value. It's the difference from this value to this value, right? That is how much I'm extracting. And so the way we write that is we're going to write that this is I systole minus I diastole, and that is equal to, so this I didn't need to write. This is just this. I don't need to write it. But this one I will write it as, oh, I don't have to write it. No, I did write it. It's going to equal I sub 0 times e to the minus a static plus a dynamic minus e to the minus a static. Okay. I took this and I subtracted this and I just pulled out the I0. I just pulled out the I0, right? So, and this is what I'm calling the AC signal. It is very much related to what comes out of the high pass filter. Okay. I built a low pass filter and I built a high pass filter. This is what's coming out of the low pass. And this is what's coming out of the high pass. I have both these signals to work with. And now comes the interesting part. I'm going to take the IAC and I'm going to divide it by the IDC. Okay, this is an interesting part. And what am I going to get? Well, I'm going to, that's this divided by this, right? I'm going to, can I do that? Yes, I can do that. Because I have this signal and I have that signal and I have digitized it, right? We're going to use a microcontroller soon. It's a division operation, right? You don't build that in a circuit, you would do it digitally, but I can do it. And what I would get is e to the minus a static plus a dynamic minus e to the minus a static over e to the minus a static. Okay. My little notes while my son was playing Pokemon. You may wonder how he did in this Pokemon tournament. Well, it turned out there was supposed to be a kids division and a grown-ups division, because grown-ups do this too, but there weren't enough people. So he had to play against grown-ups. And these grown-ups are like, they're prepared. Like they have these decks with the covers and these nice little markers and all that. And they have been investing a lot more in their Pokemon deck, Pokédeck, whatever they call it, than I have given my son. So they're coming in with all this extra stuff. So he beat the kids he played with, and he did good. He put a good fight against the grown-ups, but he wasn't quite ready to do it. Anyways, I'm deriving the stuff. And now something interesting happens where this divided by this, right, it's the same term. So that's going to give me a -1 because I'm subtracting it. Now this is, you have the exponent and I'm dividing by the exponent, so it ends up being a subtraction, right? Like e to the a plus b divided by e to the a, we just left with e to the b. Make sense? So here I'm going to get e to the minus a dynamic, which is IAC over IDC. Okay, now there is a little identity we now apply, which is, I'll put it in green, which is that e to the minus x is approximately equal to 1 minus x for a small x. All right? So e to the minus very small number is approximately equal to 1 minus a small number when x is small. And this seems a little bit out of the blue, but we're going to run with it because it serves a very important function. It is a simplification that happens. But what this allows me to say now is that IAC over the IDC is equal to, so this is the x, right? This is the x. X is minus a dynamic, right? So what I'm going to get is 1 minus a dynamic minus 1, but that is equal to a dynamic. Okay. And the point of this exercise was to strip away this e to the power. So now I have a rather simple equation. I have and what's a dynamic? Let's not forget what a dynamic is. I'm going to put a red around it. A dynamic is this term. You could say, well, why didn't you just always put that into a? It would have been a lot messier, right? If I had written this into every single a dynamic, and if I had written this into every single a static, this would have been very painful, right? But that was what I was carrying through in my head. But now, oh, okay, now I'm ready to substitute it back out. And now you can see what we get. That IAC over IDC, and to be clear, this is a quantity that I have. Okay, I took out the AC, I took out the DC out of my filters, and then I divided it up. So this is a quantity, I have it, is equal to a dynamic, but a dynamic is equal to that term. So a dynamic, and I'm going to slightly switch my notation here, is equal to the concentration of deoxyhemoglobin times the absorption coefficient of hemoglobin times the length. I'm going to put the length out here for a second. Show you why. Plus the concentration of oxyhemoglobin times the absorption coefficient of oxyhemoglobin, and I can put all this times the length, right? Now I finally pulled out this length. So you see what you have here. You took this voltage, to be very clear, you took the voltage. You put the voltage through a high-pass filter and a low-pass filter. Not complicated. Once you have these results, though, you did something, and then you save this, right? You save it in Excel, you save it in MATLAB. This is a series of numbers. This is a series of numbers. And then what you do is you divide these numbers in each time point by the DC numbers. Well, the DC is just a number, right? It's just a mathematical alteration. AC divided by, that's what, I want to make sure that this is sitting in your instrument. You have this number, right? You have this number, and you're realizing that this number is equal to this. And of course, what do you want? You want SpO2, For SpO2, you need this and this, right? We want, what do we want? We want this, and we want this. This is a number. What do we know? So what do we know? I'll show you what we know, right? What do we know? We know this, we know this, we know this. We do not know this, and we have this, and we have this. Oh. So we're not there, right? Because we have three unknowns. Right? We have one number, but I don't know how much deoxyhemoglobin Emily has. I don't know how much oxyhemoglobin Emily has, but I also don't know the dynamic length of her capillaries. Okay, what do we do? Someone said it already. How do we get rid of this L? Go say it. You said it before. How do we get rid of this? I want to get rid of this L. We know how to get rid of this L. What do? Use 2 LEDs. You notice that up to now, wait, what frequency was this? Oh, I didn't say. So let's do it twice, right? This is what we're going to do. We're going to repeat this whole thing for red, and infrared. And what that's going to do is it's going to give me 2 equations. I promise we're almost at the end of this, all right? I promise we're at the end of this, right? My son's like in a second Pokemon tournament here. I'm just like, okay, I have to work it all out. It's fine. And I also promise you that I think this is the simplest way to explain it. Okay? This is not, this is already sort of a reduced explanation. So what I'm going to do here is I'm going to say IAC over IDC, and I'm going to say, no, I did this for red. And all I need to do now is just need to update this equation to say concentration of deoxyhemoglobin times the absorption coefficient of hemoglobin at red light plus the concentration of oxyhemoglobin times the absorption coefficient of oxyhemoglobin at red light times L. That's why I gave you the quiz. I needed you to do this. I wanted you to be ready for this. You did this on your quiz, right? That's why I gave it to you, right? I wanted to tee this up. Now you know what this is, right? But I say, hold on, stop. Turn the light off. Now shine infrared. I could do that, right? Reset, do infrared, fine. So now what I'm going to do, I'm going to say IAC over IDC at infrared is equal to, well, what's that going to be? It's going to be the same concentration of HB times the absorption of HB at infrared plus the concentration of oxyhemoglobin plus the absorption of oxyhemoglobin at infrared over L. This is, I have this. It's a number 3 that's sitting in my computer. I have this. It's another number, 1.5, that's sitting in my computer. I know that we did a lot of steps here, right? But just remember, high pass, low pass, divide it up, do it twice. So now you have the number 3 and you have the number 1.5. Well, if I have 2 numbers, I could divide those numbers? I could divide those numbers. I mean, I already did one division. I'm going to do another division. And this is the key to pulse oximeters. Pulse oximeters work by what's called a ratio of a ratio. Because now watch what happens. If I take let's call it AC to DC. Which one goes on top? Red. And I divide it by I of AC to DC for infrared, I get this equation. I'm going to get well, I'm just going to do it here because I'm just going to rewrite it. If I do I of AC to DC red over I of AC to DC infrared is going to equal this divided by that. Right? This is a number. If this was 3 and this was 1.5, I now have 2. And I can say that 2 is equal to all this. Sayonara length. Just like before. Just like before. See that? We got rid of, and that's why it's the ratio of the ratio. Okay, now let's see what we know. We know this. We know, no, we don't know this. We know this because I gave you that number here before, right? You know it, right? You know this. You know this one, you know this one, you know this one. Very good. So, are we done? How many equations? 1. How many unknowns? 2. Oh. So, the pulse oximeter can't work. The pulse oximeter cannot give you the concentration, it cannot tell me what the concentration of oxyhemoglobin is in Emily's blood. And a pulse oximeter cannot tell me what the concentration of deoxyhemoglobin is in Emily's blood. And what I'm telling you is true. It cannot. If it cannot give me these parameters, then we're done. It can't give me the SpO2, right? Let's see. Right, Emily, you want to put it on? Let's see. And Adrian here is a paramedic, so if we have a problem. What are you, EMT? Yeah. EMT. What's it reading?
98.
98. So it's telling us that Emily is at 98%. And it gives us, and we got Emily's heart rate as well. Very good. Wait, but it can't do that because it doesn't have these parameters. And now there's the trick. And this is a cute trick. And this is why I left this up here. You see, this, I don't need to know the concentration of oxyhemoglobin in Emily's blood. I don't need to know the concentration of deoxyhemoglobin in Emily's blood. Right? If I was a chemist, maybe but I'm a biomedical engineer. I need to know her SpO2. See that? Emily, I don't need to know, does Emily need to go to hospital or not? I don't know. If I just gave you the if I gave you the amount of oxyhemoglobin in her blood, Adrian wouldn't know whether she has to go to the hospital or not. This is what we need. Remember? Medical device, sensor, display, and all importantly, the decision. Sorry, that's really messy. Okay? So how do we get this? Watch. This is this. And this is this. And watch what happens here with the math. This is as cute as math can get. Okay? Watch what happens. So first I'm going to substitute this. And so that's going to be 1 minus SpO2 times the concentration of HB total. I'm going to have to give myself a little bit more. Let me start here. This is going to equal, the first term is going to be 1 minus SpO2 times the concentration of HB, let me just write T for total, times the extinction coefficient for deoxyhemoglobin in red, that's not going anywhere, plus, okay, this one is this one, so now I'm going to say SpO2, let me just put that in parentheses so we see where it hangs, times the concentration of HB total times the absorption of HbO2 at red. I don't know if you see what's happening here. And then I'm going to do over, okay, I have this one again. So that's going to be 1 minus SpO2, right, times the concentration, times Hb total, times the extinction coefficient of Hb at infrared, plus, and then I'm going to take this one again. So that's going to be, once again, SpO2 times the concentration of Hb total times the absorption of HbO2 at infrared. See, I was leaving this here for a reason. This was an odd expression. It really is odd until we suddenly plug it in here, and then something happens. Hb total, Hb total, and Hb total, and Hb total cancel out, and that's the trick. So what I can do now, let me get a little orange, is we're going to take this out, we're going to take this out, we're going to take this out, we're going to take this out. Let's erase it. I'll fill in the gap with a little multiplication. Let me go ahead and remind you what we know. We know this, right? We know this, we know this, we know this, and we know this. Let me mark the unknowns. Where'd my red go? Here. Let me mark the unknowns. Unknown, 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 unknown. So to be clear, this is a number, 1.5. And this is a number 3, and this is a number 6, and this is a number 2, and this is a number 0.1. Don't worry about the complicated notation, right? So if I were to give you this, how many equations? Still 1. How many unknown? 1. And that's how the pulse oximeter works. That's why I had to hold this here. A pulse oximeter doesn't know Emily's oxyhemoglobin concentration, but it doesn't need to. Is this what now you're saying, is this what an actual pulse oximeter does? It does. An actual pulse oximeter takes a ratio of a ratio. Now, there is 2 more equations I need to show you. Okay, now I can erase. Finally, I can erase this. I was holding on to it this whole time. This ratio of ratios, I'll write it here. This IAC/DC for red over the IAC to DC for infrared will be referred to as R. And R is equal to, and there's different ways you can, well, I need to simplify it. Well, I simplified it, so here it is. There's different expressions for it. So one would be the extinction coefficient of deoxyhemoglobin at red plus the extinction coefficient for oxyhemoglobin at red minus the extinction coefficient for deoxyhemoglobin at red times SpO2 over, it's the same equation. The terms have just been rearranged to pull out the SpO2 over the extinction coefficient of deoxyhemoglobin at infrared. I think this is symmetrical arrangement. This is going to be the extinction coefficient of, that's the way I wrote it, never mind, negative deoxyhemoglobin at infrared plus the extinction coefficient of oxyhemoglobin at infrared times SpO2. All right, this is just group pulling out the SpO2 and giving you the extinction. Good thing, by the way, the SpO2 doesn't fully cancel out, right? Or we wouldn't have it, right? And it turns out, and you'll see different versions of this, like the E's might be swapped and this is a negative, right? But they're all going to be the same. It's always going to be the same terms. And then you can actually say that the SpO2, if you were to solve this for SpO2, right? Because we have here an equation, right? So let's rearrange all the terms so we get in terms of SpO2 is equal to, and I'm not going to derive this, I'm going to give it to you, it's going to be the extinction coefficient of deoxyhemoglobin at red minus R times the extinction coefficient of deoxyhemoglobin at infrared over the extinction coefficient of deoxyhemoglobin at red minus the extinction coefficient for oxyhemoglobin at red, yes, minus R times the extinction coefficient of deoxyhemoglobin for infrared minus the extinction coefficient of oxyhemoglobin at infrared. Okay. All right. We put a square around it because it's boring. It's not that complicated. This is a number like 3, right? These are just numbers. So every time you see an E, just plug in a number, right? So you'd end up with something like 3 minus R times 2 over 6 minus R times 6, right? It's just numbers. What is R? R is the thing, R is the ratio of ratios. So what you do is you develop an instrument that does a high pass and a low pass, and it does it for red and infrared, and it does a ratio of ratios. And then you get a value out of your instrument that's called R. And then you don't have to know the math. Just take that R that you built and plug it into this equation. And the thing that will come out is Emily's blood oxygen. So the whole point of this derivation isn't so that you could memorize it or I could test it on you. It's that you understand like that it's all Beer-Lambert. That the only thing you needed to accept was Beer-Lambert. And once you accepted Beer-Lambert, right? Now there's a little tricks, right? Like the AC and the DC and this little substitution we did here. Little tricks that maybe you know would be hard to anticipate on your own, and voila. Except, of course, just like with your thermistor project, the equations don't work. Because in reality, so what they do in reality is they calibrate. So sorry for those of you who are paying attention. So sorry. But what they actually do is they calibrate. So they say SpO2 is equal to some constant A that they calibrate to times B times R. So what they do is they extract the R. The R is still the ratio of the ratios. So I didn't waste your time. The R is still this. But when they go from R to SpO2, they don't use this equation. For each pulse oximeter, right, they will calibrate it. And there's different ways. You'd have to use a gold standard and you'd calibrate it. So sorry, okay? But yes?
For devices like this from company to company, is there like a FDA standard for like how they calibrate it?
Good question. Is there an FDA standard for how they calibrate these devices? I'm pretty sure there is. These pulse oximeters are so common. then my guess is that there are multiple FDA standards, IEEE standards about pulse oximeters. So if you want to start a pulse oximeter company, you could. And you probably have a follow-up question about, do they calibrate it across all kinds of people? That I don't know if the regulations ask for that. All right, but there is something else. I'm just going to give you one more nugget. This is nice, but there's something else that I didn't tell you about that the pulse oximeters do that to me is sort of kind of interesting in itself. So it turns out Beer-Lambert doesn't hold for biology because nothing holds for biology, right? So the Beer-Lambert said that, let's rewrite it. It says that I is equal to I sub 0 times e to the minus absorption coefficient, right, minus a. I mean, that's sort of the standard, right? That's the most basic Beer-Lambert law. Now I'm going to show you all the ways this fails, and I'm going to show you that none of them matter. So one of the ones is when you build your light source, right? So you have, I don't know, you have like a 9-volt battery, and it's connected to some sort of LED, right? And so for the voltage you put in, you get some light out, right? Seems pretty important to know that. I mean, if you don't know this, aren't you cooked? I mean, what cooked, right? I mean, everything we did here had to do with calculating I. But if I tell you, if you say, oh great, I built a pulse oximeter, I'm ready to do my math, how much current did you put in? I don't actually know because there's a lot of issues. Why would you not know? Well, I don't know, what if my watch shifts a little bit to the right? What if the way the light shines is not in one direction, it's in multiple directions? So you're not sure. So what I'm going to add here is I'm going to say we don't know, and I'm going to add a constant of, let's say the amount of voltage that you put in times this sort of LED X term that you don't know. Oh, so we don't know how much light we put in. Nope. Now, when the light comes out, we convert the light to a voltage, right? And so it's pretty, I mean, if you tell me how much light came out and you say, well, I don't know, why do you not know? Well, I didn't know because I'm not really sure how my photodiode works, and it turns out that in reality, there's a lot of different kind of issues. All right, we don't know. So what I'm going to say here is that this is equal to, let's say the actual light that came out times my, something about my sensor that I don't know. So I don't know what I put in, and I don't know how my sensor works. Interesting. Now it turns out there are other issues as well. This assumes that the sensor is right here. And the emitter is right here, right? Doesn't work that way, right? Not only that, but in this material here, the sensor and the emitter are on the same side, right? Apple couldn't put the sensor on this side. I think it would have been complicated with the band, which means the light goes in and then it comes out. So it's not what I showed you like this. The light actually goes in and then it bounces back. And the amount that it bounces back from the sensor to the emitter is governed by a lot of complicated things, which people express as a geometric factor, G. And here's the problem. Even if I could figure out the G on me, when I gave it to Emily, she wouldn't have the same G. Why? Well, she wears her watch looser than I do, and a bit at an angle. And also, I don't know, she has other kind of issues that factor into well. So this is G as well. And there's also a fact that this is not transmission, it's scattering. And so Beer-Lambert's law has to be modified with another term called S. And then we get, finally, e to the minus. And let me break this up into the astatic and adynamic, right? We have our A dynamic. We know what the adynamic term is. That's the thing we always cared about. Minus A static. And it turns out that this geometric factor, I've also seen it represented here. So thank you very much, test tube. We don't work with test tubes. This is the issue. And I actually, let me show you what I don't know in orange, what I don't know. I actually don't know this. You could say you could figure it out, but you can't. I don't know this, I don't know this, I don't know this, I don't know this, and I don't know this. Everything just fell apart. Do you see it? Except, yeah.
Do you feel that having all this emphasis make it less reliable?
Complete. What if this is 20 on me and 3 on Emily? And you don't even know. And then Mujtaba does it, and it's 5 on him. If we lose our equation, if we can't use Beer-Lambert, what are we talking about? So here's the thing. You see the step where I took IAC and I divided by IDC? You know how I took all these ratios of ratios? You know what ratios of ratios do? They knock out things that exist in both cases. And so what's interesting is, by doing this ratio of ratios, right, everything that exists in both cases is knocked out. So I don't know my geometric factor compared to Emily's. But I do know that once I put this watch on, I've set a geometric factor. The G is set. For me, right now, it's 3.7. So 3.7 appears here. But 3.7 divided by 3.7 is 1. And when Emily puts this on, her geometric factor is 6.2, which we don't even know. So she has a 6.2 sitting here. But once I do the math, and I do the high pass and the low pass, and I divide it up, it's sort of like imagine if the light was twice as bright. If the light was twice as bright, right? If I was twice as bright, well then this would be twice as bright, and this would be twice as bright, but I'm just dividing them out. And so there is this amazing, so the fact that we can put this on, all right, and tell you with tremendous reliability what your SpO2 is a remarkable feat of biomedical engineering, and it's very fortuitous. See what I'm saying? And so that's why I wanted to go through this math. I wanted to show you this. There's not a lot of things. I mean, one reason you could say that the first thing Adrian does when he pulls up in an ambulance is put this on people is to say because it's very useful, which is true. But the other explanation for why Adrian puts this on for people is he doesn't have anything else. You put it another way. We're going to talk about how to measure blood glucose, right? You could say, oh, that's cute. What about blood glucose? If you can measure blood glucose with a watch, okay, you are a multi-billionaire. If instead of going to a doctor's office and them drawing all my blood, you can put this, and on the screen there goes potassium, right? Blah, 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 insulin, glucose on a screen, $1 billion. It's really, really hard. We'll talk about why. It just happened to work out for pulse oximetry. It happened to work out. You see what I'm saying? It just happened, this little thing and this thing, it just happened to pop out. But it's not something you should expect normally with optical measurements. So I think one reason why we always use pulse oximetry, one, is because it's very useful, but B, Adrian doesn't have anything else like this. There's nothing else like this that can measure anything else, right? And so, all right, so that's it for pulse oximetry. What we're going to do next is we're going to be talking about measuring other things. We'll talk about measuring glucose. That's a big one. We'll talk about a few other things of how we measure things, okay?